Okay, the recording is started. Okay, so hello everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am currently your NPTEL PMRF TA for the course Introduction to Probability Theory and Statistics. This course is offered by Professor S. Dharmaraj. He is currently a faculty in IIT Delhi. Okay, this is the second week of a 12-week course. In last week, we will discuss about the basics of probability. Okay, so just take a small recap about those, and after that, we will discuss about the week second course. Okay, anyone have any doubt or they want to discuss or ask anything, they can directly ask me. Okay, okay, then let's start. Okay, like la last week, we will discuss about the basics of probability. In which we will discuss about the random experiments, events, sample space, axiomatic definitions of probability, conditional probability, independence of events, mutually exclusive events, and Bayes theorem, etc. Okay, so let's just give some recap on those topics. Like random experiments are, okay. I hope everyone sees my uh, screen. Is it feasible now to everyone? Okay, random experiments are like an experiment is said to be random if its results cannot be defined beforehand. Like we do not know about the what comes when we perform that experiments. Okay, but we know about what are the possibilities of events that are going to happen. Okay, those are called random experiments. Like while tossing a coin, we know about whether either head occurs or tail occurs, but we do not have the information that under that particular trial which phase is going to show. Okay. Similarly, sample space are defined as the it is defined as the collection of all possible outcomes. Okay, suppose we are rolling a die, then all the possible outcomes are either 1 or 2 or 3 or 4 or 5 or 6. So a sample space consists of 1 to 6 elements. Okay, like for in that case, we will write like this. These are the sample space for rolling a single die. Okay. Uh, we will also discuss about the sigma field or sigma algebra. Okay. So let me write the condition for sigma field or sigma algebra because these are also used in the second week. Okay. Sigma field or sigma algebra is a collection, capital F, curly F, whatever you say. Okay. Collection of sub F, which is a subset of the sigma, which is a subset collection of subset. Okay, a collection omega of subsets of the sample space omega. Okay, then this is called a sigma field if it follows three conditions. Like the first one is uh, the sample space should belong to the same field. Okay, the second one is like if any a any element or any event A belongs to this F, the sigma field, then this implies its complement should also belong to the same field. Okay. And the third one is like if we have an arbitrary number of events like A1, A2, up to, okay, which all belongs to F, then in that case, uh, the union of AI should also belong to F. If these three conditions are satisfied by any collection of subsets of omega, then that subset of omega is called a sigma field or sigma algebra. Okay. Uh, the next is like the definitions of probability, axiomatic definition of probability. These are already discussed in the first week actually, just I'm naming them. Okay. Axiomatic definition of probability, the statement will be like this. Suppose we have a sample space omega. Okay. And suppose we have sample space omega and corresponding this sample space, we have a sigma field. Okay. And we define a real valued function. We define a function. Uh, we define a function capital P, which is a real valued set function. Okay. In such a way, in such a way that it like maps the element of field to real number. Okay. So it is a probability function, and it must follow these three conditions. The conditions are like the first one, the probability of event A should always greater than or equal to 0 for all A belongs to this F. Okay. The second condition will be like the probability of the sample space comes out to be 1. And the third one will be like, it is a conditional statement actually, the last one. Like if we are A1, A2 up to infinite numbers. Okay, countably infinite events are there. Okay, these are mutually exclusive or disjoint. If these are mutually exclusive events, okay, and these are belongs to F. If this condition holds, then the probability of union of AI must equal to the summation of the individual probability of AI. Okay. If this condition holds, then this also true. These three conditions hold by this function P. So this function is known as probability function. And this is the definition of axiomatic definition of probability. Okay. Then we will discuss about lot of examples about these things. Sir has already discussed many things actually. Okay. So we will discuss about the second week lecture now. You know about the mutually independent event when two or more than two events are said to be independent when the probability of their intersection is equal to the product of their individual probability. Okay, like let me write mutually independent events, then probability of A1 intersection A2 intersection AN is nothing but the probability of A1 into probability of A2 up to probability of AN. So the probability of the intersection equals the product of their individual probability. Then those events are said to be mutually independent, and pairwise independent is also there. Like if probability of AI intersection AJ equal to probability of AI multiplied by probability of AJ for all I is not equal to j, then it is said to be pairwise independent. Every two elements are independent, hold independent property. Okay. Then there is Bayes theorem, like conditional probability is also there. Like probability of A given B is defined as the probability of A intersection B divided by probability of B. Okay. And modified version of this, the conditional probability is also a Bayes theorem. Okay, in which we are given some prior probability, and with the help of those prior probability, we are able to calculate the posterior probability. Okay, that means, yes, anyone want to ask anything? Okay. Okay, then with the help of those prior conditions or prior information, we are able to calculate further probability. Those are called posterior probability. Okay, and this is done with the help of either conditional probability or the Bayes theorem. Okay, so these are all up to week 1. now we will discuss about week 2 content. Okay. I hope everyone have at least seen some of the videos, okay, of week 2 lectures. So in week 2, we will mainly discuss about the definitions of random variables, the cumulative distribution functions, types of random variables like discrete, continuous, and mixed type of random variables are there, and PDF and PMF like probability density function and probability mass functions. Okay, and the type of distributions of functions of random variables. So these like topics are discussed in week second. So we will discuss about some definitions and formulas, and after that we will solve some numericals based on those topics. Okay. If you have any doubt like regarding assignments or anything, then you people may ask. Okay. So we will start with random variables. Can anyone define what is random variables? It should be interactive session. Let's talk. If anyone wants to like define or say anything about random variables, like we are open. Okay. So look, random variables is not a variable. Okay. It is like not a variable, first thing. It is actually a function. Okay. So random variable is a function. It is a function. It is a map. A map from where? Like in simple language, we can say that it maps sample values or sample elements. Sample elements are come from the omega. Okay. To real numbers. Okay. A random variable, it may, we can say that it is a converter, like it convert a random sample omega value or omega element of omega to a number. It assign those element a number. Okay. It is a general, just a simple thought. Okay. Actual definition, we can say like this. Let we have omega, a sample space omega, a field, sigma field F, and the probability function P. So it is a probability space. We have a probability space. Okay, if let this be a probability space. Okay, then a real valued function. A real valued function. A real valued function, like let's define it X, which is from the omega to a real number R. Okay, it's said to be a random variable. Okay, if if the inverse function of that x, if inverse function of that x on semi-closed interval also belong to the same field F. Okay, then if any function defined from omega to real number, okay, then the inverse of those function on a semi-closed interval should also belong to F. Then those X function is known as a random variable. Okay, and why do we call it a random variable? Because actually it is a real valued function. Okay, and it comes from a random experiment. Okay, when we perform random experiments, then only we are able to like formulate the omega. Okay, then that's why we call it a random variable. Okay, so this condition is the gives the definition for the random variable. If we need to like check whether a given function is a random variable or not, we should like check whether this condition holds or not for the defined. Okay, we have some remarks regarding these random variables. Like the first remark is like x is a okay, x is a real valued function. Okay, it is actually already defined. X is a real valued function. It is called a random variable. It is called a random variable if like if it is defined, not if is not there actually. It is defined from like omega to the of real number r. Okay, and omega comes from random experiments. Okay, so it is called a random variable. Okay, this is the one thing. It is also like one more thing we need to keep in mind, like it is also known as measurable function. Okay, so x is a random variable and it defines on omega and the field. So it is also known as like x is a measurable function with respect to the field f. Okay, and okay, and also we say that okay, let's give one example. Okay. These are already discussed in the lecture actually. Okay, so let's take an example like define omega in such a way it has three elements a, b, and c. Okay, then can anyone define a like field, any kind of field for this particular omega? Anyone? Look,
Phi
field.
and the
Yeah,
whole set.
yeah. Phi and exactly the null set and the whole set or sample space. It is called like trivial. It is called trivial sigma field. Okay, a field must define the above three condition that we have already discussed here. These are the three conditions that should be defined, that must be like valid. Then those field is said to be sigma field. Okay, for this sample space omega. So here we can define more than one sigma field for the same for the same omega. Okay, so like we can define f1 should also be there. Suppose we define f1 in such a way that it contains the null set, and suppose the element a is there, and b and c, and suppose the last one is omega. Okay, and then we define a random variable x such that x should be defined like this. Omega is any element from the sample space only. Okay, x omega or xw you may say is like this 0 and 1. It like takes the value 0. Okay, let me write one more thing actually. Like the random variable x from this to it is just a notation actually, but I should write here. Okay, in such a way that x of w equals 0 or 1 when 0 occurs when w takes the value a and w takes a value b or c. Okay, this is a function we have defined in such a manner. Now our aim is to check whether the given x function is a proper random variable. हमें ये check करना है. Okay, sorry. We need to check this whether the given x is a random variable or not. For that purpose, we have a definition for the random variable that we have written here. Okay, this is this star condition should follow for the x. So let's start from here only. Okay. So, okay, let me redefine. Like inverse image of x. Okay. On a semi-closed interval minus infinity to any arbitrary number x. What are the values of these? So we have like definition here, x equal to 0 and x equal to 1. Okay, so we have 2 points, two jump points we can say. Okay, so the first one is like suppose we have x is less than 0. In that condition, if x is less than 0, this is minus infinity, this is infinity, this is 0, and we have x which is less than 0. So x may lie somewhere here only. Okay. So our random variable x in that case, when 0 occurs when x equal to a, sorry, w equal to a. So in that case, like we are not getting any value. So in that condition, we can define the x inverse function as nothing but phi function. Okay. Now the second condition may arise when we consider the value of x is uh, lie within 0 to 1. Because we have 2 points, 0 and 1. So we will move around those 2 points only. So we have considered x lies between 0 1. So in that case, suppose we have the value of x here. So in that case, it contains 0. It contains 0 implies omega may be possible have a as its subset. Okay. And the next one is like x greater than or equal to 1. Okay, greater than or equal to 1, or we can write it like this, greater than equal to 1 is infinity. Okay, so now suppose here it is 1 actually. So now the last x may be here. So in that condition, it contains 0 and 1 both. It contains 0 and 1 both because uh, minus infinity to x contains 0 and 1 both. So in that condition, it is gives 1, B and C and A also. Okay, so it gives all the value actually if you like say. So we have omega in that scenario. So we have sample space omega in that scenario. Now what? Now we need to see that this okay, let me. Now this belongs to F. This A belongs to F. Here we see that F is defined in such a manner. Okay, and omega is also belongs to F. So all three belongs to F. So we say that X follows the condition. So at last, X is a random variable. Okay, I hope it is clear. No? I think here the inverse image gives either phi or A or sigma. Okay, sorry, omega. Okay, and all these three belongs to F, which follows the condition for the definition of a random variable. So we say that X is a random variable for this omega and this field F1. Okay, random variable for the field F1. Okay, again, suppose we define another random variable for the same field. Okay, we take the case second actually. We define the another random variable for the same omega and same field f1. Then let's see. It is like this, 0 and 1. Again, w equals b and w equals like a or w equals c. Okay, now the random variable or the function y may define in such a manner. Again, we define like the inverse function x inverse of, sorry, we need to write y inverse because we have written y inverse and semi-close interval up to x or y. You can take the value small y or any arbitrary value. So the possibility is what? When we consider x is less than 0, in that case we get phi. If we take x lie between 0 to 1 including 0, then we have the element b as, and if we have like infinity, then again we have omega. Okay, now if you remember, the f1 field contains actually phi a, b, c and omega. Okay, so here you see that this belongs to f, this belongs to f1, and but this does not belong to f1. So it does not follow, the y function does not follow the definition for the random variable or the star condition we have mentioned above. So we say that follow the definition of random variable or the star condition. So y is not a random variable for like the field f1 and omega. Okay, so it is not a random variable with respect to field f1. Again, if suppose we define the uh, okay, the same the one another field for the same sample space omega, then maybe we can define like this. Na? We have already discussed this in class. Like this is also f2 is also a sigma field for the sample space omega. Okay, but in that case, if you are going to check, then you will find this y is a random variable for the field f2 or with respect to f2. So I'm not going to like check this, but it if you want to check, you can check. Okay, so here we find out y is a random variable with respect to the sigma field or sigma algebra f2, but it is not f1. And here we see that both f1 and f2 comes from the same sample space omega. Okay, and this like uh, we can, okay, like we can say, wait, let me check. Okay, yes. So we have more than one field. Okay, and for the same sigma, for the same omega or sample space, and for the same sigma field, one function may be a random variable and the other may not. Okay, so how can we like define a sigma field such that all the variables, all the functions that are defined in those form are random variables? For that purpose, we know about the like the power set, the power set, which is the largest set, okay, which is the largest set, or sorry, which is the largest field. Okay, those are the power set. Those are that set is actually the, okay, wait, any function, maybe we can define any function that must follow the definition of random variable, or that is a random variable when we have considered the sigma field as our largest set or power set of the omega. Okay, like we can take here again the example, same example. Suppose omega equal to like a b c, F. Okay, let me write here. F here phi. We need to like collect all the subset of the say, omega. So it may either A or B or C, or we will take AB, BC, CA, and ABC. Okay. Now this contains, if we define X or we define random variable Y, in both the cases, this particular field F is a the definition, it follows the definition. So we say that X and Y both are random variable for the field F. Okay. Now one more remark is there actually. Like any real valued function will be a random variable. Okay, that's already we have discussed. Like any real valued function that are defined from omega to f. Okay, any real valued function will be a random variable. Okay, will be a random variable with respect to largest sigma field, which is also known as power set of omega. Okay, so this is one example. Okay, now we will discuss about the random variable. Now we will discuss distribution function. Okay, again we are going to discuss a function which follows some property. Okay, so a real valued function we are going to represent it with capital F only, because in further classes or further we will use the CDF as capital F. Okay, so a real valued function capital F satisfying the following conditions. Okay, the first one is like the value of the function lies between 0 to 1, including both for all x. Okay. The second condition will be like it is monotonically non-decreasing. Okay. That means like if x1 is less than or equal to x2, this implies, sorry, this implies f of x1 less than or equal to f of x2. Okay, this is the monotonically non-decreasing function. Okay, the third one will be like the value of the function at minimum and maximum. The limit minus infinity x must be 0, and the limit x tends to plus infinity equals 1. And the fourth one, it is a right it is a right continuous. Okay, so if these four conditions are satisfied by any function, then that function is a distribution function or a cumulative distribution function. If you are dealing about probability. Okay. Now we can like solve some questions on the basis like whether we define some capital fx function, and we will check whether that given fx is a CDF or not in for next some time. Okay. Sorry, give me a minute. Okay, we have one more example. Okay, so let's check. Okay, this is already discussed by sir. Suppose we have perform a random experiment. Okay, tossing two coins simultaneously. Okay, so in that, if I'm writing like this, tossing two coins, and I'm not saying about the nature of the coin, then it is like by default we assume that it is a fair coin or unbiased coin. Okay. In case it is biased or unfair, then we will mention those things in our questions. If we are not mentioning these type of words, then that means it is unbiased fair coin. Okay. Similar for dice and cards, etc. Okay. So what are its sample space? Can anyone tell me? When two coins are tossed, then it is either head on both, head tail, tail head, or tail tail. These are the only four possibilities. Okay. Now, can anyone like define uh, all the subset of this set, or can anyone formulate a power set for this? How many elements are there, by the way? Anyone? Am I audible, na? At least confirm this. Okay. Let me write this like beneficial for us. Okay, I'm not writing all this. One like single elements are there, then double elements are there, then triple elements are there, and at last there are the simple space omega. Okay, and the cardinality for this is 60 because we have four elements. Then 2 to the power 4 is the number of subsets of that particular set. So it comes out to be 16. Okay, now again we define a random variable. Can anyone define the random variable for the omega? Anyone? No. Like random variable we define like this, na? Since we are performing the tossing two coins and either one head or two head or no head are there. So we can define like the number of heads. We know when we perform two coins, toss two coins, either there is both tail, there is one head and one tail, or there are two tails, two heads are there. So number of heads are there. So the possible value for x is either 0 or 1 or 2. So let's define the random variable x, 0, 1, and 2. Okay, when it comes out to be 0 head, then when w equal to, we get double tail, then it comes out to be x equals 0. When it comes out to be ht or w equal to ph, then we have x equal to 1. And x equal to 2 comes when h is there as our outcomes. Okay, these are the function we are defining. Okay, now our aim is to check whether this x function is a random variable or not. Okay, so for the random variable, what we are going to do? like we need to define the inverse function of x. Okay, on a semi-closed interval omega x. So we have 0, 1, and 2. So we have three boundaries are there. 0, 1. In the previous example, we have 0 or 1 only. So we have two boundaries. 0 less than 0, 0 to 1, and more than 1. Okay. Here 0, 1, 2 are there. So less than 0, 0 to 1, 1 to 2, and 2 to infinity are there. Okay. So okay. The first one is x is less than 0. So again, if you are not like able to do, so 0 minus infinity plus infinity is there. X is taking any value less than 0 here is there. Okay, so less than 0 there is no definition of x. So we have a phi function for that, or null set or empty set is there. If we have x between 0 to 1 including 0, in that case we have taken some value of x between 0 to 1. Suppose here is the x. Okay, so in that case it contains 0 only. It contains 0 only. So there is 0, 0 only. So it has 0 corresponding to the element tt, double head, double tail is there. And 1 to 2. Okay, the x values lie between 1 to 2, include excluding 2. So we have x like here. So it contains 1, it contains 0, it contains these are like the left part before the x. Okay, so it contains 1 and 2. So 1 and 2 contains three elements only, if you can see. So it is either head tail or tail head or tail tail. The three elements are there only. Okay, and if we take like x, sorry, if we take like x is greater than or equal to, then we have omega. The whole sample space are there. Okay, so this uh, this phi belongs to f. Yes, this t belongs to f. This also belongs to f, and this is again. So this follow the definition. So we can say that x is a random variable with respect to the power set or the sigma field f. Okay, now we confirm that the given function x is a random variable. Now our next aim is to define the distribution function. Okay, the cumulative distribution function. So the cumulative distribution function is actually defined like this. Suppose f is a cumulative distribution function. Okay, for the random variable x, these are the standard notation for that. So it is nothing but the probability that x is less than or equal to x. Okay, this is the definition for the cumulative distribution function. Okay, now since x is a random variable, so let's define. So fx of x may be we have x is less than 0. In that case, it comes out to be 0. When the value of x lies between 0 to 1, including 0, in that case, we have only one element, so it comes out to be 1 by 4. Now, x lies within 1 to 2, including 1 and excluding 2. In that condition, we have 3 of the 4 elements from the sample space. So in that case, we say that the cumulative probability, not probability, the cumulative probability is 3 by 4. And when x is greater than or equal to 2, the CDF will be 1. Okay, and you can see that it is positive. Fx is a CDF because it is positive. It minimum value contains 0 and the maximum value of x contains 1, and it is continuous to the right also. If you are like going to see this, we can like draw the graph even. Less than 0, it is 0. Less than 0, it is 0. Okay, so 0 to 1, it is 1 by 4. suppose 1 by 4, 2 by 4, 3 by 4, and 1. 1 by 4, 2 by 4, 3 by 4, and 1. So 0 to 1. Okay. 0 to 1, it is 1 by 4. And just after 1 to 2, it is 3 by 4. Okay. And more than 2, it is 1. So this is the graph, the nature of the graph for the CDF of this particular. Okay. And here we see that if you can see, it is continuous to the right. The continuous to the right means like the function value. Okay, let me write here. Limit. Suppose we are going to check whether the given function is continuous to the right at x equal to 0. At x equal to 0. So we can write in this form, plus for right and minus for left. So limit x tends to 0 fx. That can also be like written as limit h tends to 0 f of x plus h. Okay. And this should be equal to the functional value at x equal to the point itself 0. If this condition holds, then the function is said to be a right continuous, okay, or continuous to the right. So this condition is actually true, if you can see, or we can draw. Okay, so this point, and before that, all the value for all the right values, it is 1 by 4 only. There again at x equal to 1, and for more than one value, it is again 3 by 4, and 2 and onward, it is 1. So it is continuous to the right. Okay, and the minimum value is 0, maximum value is 1 is there. Okay, actually you see it follows all the four property. So we can say that the given function is a cumulative distribution for the random variable x we have defined in number of heads. Okay. So like these are the questions. Okay, how we can like check whether the function is a random variable, and then like formulate the CDF for that random variable. Okay, now we will discuss about the types of random variables. Okay. Types of random variables. So there are mainly two types of random variables, discrete and continuous. Okay, and we have a mixed version of these two. So we have like three types of random variables. The first one is like discrete random variable. Okay, so a discrete the second one is continuous random variable. And the third one is mixed version of discrete and continuous. Okay, so let's define these three. A discrete random variable a random variable x is said to be discrete, like if its CDF has countable number of discontinuities. Okay, or we can say that jump countable number of jump points are there, then we say that those type of random variables is a discrete. Since it is already defined, it is a random variable, that means it follows the above property. Okay, now we need to classify those random variable in between discrete, continuous, and mixed. So if it has jump points, okay, and a CDF who have only jump points, okay, are discrete random variable only. Okay, and we can define in such a manner probability like x equal, these are the for discrete random variable, these are the notations. Okay, probability that x, the random variable capital X equal to small xi. Okay, it is defined as like probability of omega such that x of omega, the distribution function on the random variable x only, equal to xi for all it belongs to omega. Okay, And the cumulative distribution function may be defined as, for this x, the summation xi less than of x. Okay. Uh, Probability that x equal to xi. Then this is called uh, cumulative distribution function for the discrete random variable. Okay. Now we have a PMF related to this distribution only. Okay, when we are discussing about discrete random variable, then the probability density function is termed as probability mass function only. Usually we will discuss about density function, but when the random variable is discrete in nature, then that density function is known as probability mass function. Otherwise, it is known as probability density function in general. Okay, but we have two different terminologies: PMF, probability mass function. Probability mass function. Okay, it is defined as like probability that x equal to xi. Okay, and have some properties like the p value at x is always greater than or equal to 0, and the second one is like summation of p of x or xi equals 1. If these two conditions are hold, then that function is a probability mass function. Okay. Now again, tossing a coin, these are the examples of the PMF we will discuss in next some after some slides. The second one is like continuous random variable. The continuous random variable is defined is said to be a continuous if its CDF is continuous in X. Okay. A random variable. Okay. And the random variable is classified as continuous random variable. Uh, in that case, when the random variable x is a continuous function, okay, then it is a continuous random variable. Okay, a random variable x is said to be a continuous random variable if its CDF is continuous function. Okay, if its CDF is continuous function in X, then it is said to be a continuous random variable. The CDF will be like this: minus infinity to X. These are the notations how we will how we will show the continuous random variable, discrete random variable, CDF, PDF. Okay, and again, with the PDF is also there, like probability density function. It is similar in nature, like a function is said to be PDF greater than 040. Okay, and the second property will be like the integral over x. Okay, equals 1. When we are discussing about discrete random variables, we will use the notation summation. Okay, and for continuous random variable, probability density function are used, and the probability and the summation is like exchange or replaced by the integration sign. Okay. Okay, and now the last one is mixed random variable is there. Look, mixed random variable is a random variable having a jump point as well as interval as both. Okay, jump point as well as interval. Then that type of random variables is called as mixed random variables. Okay, so a random variable is said to be mixed if its CDF has both countable number of discontinuities. Okay, if its CDF has both countable numbers of discontinuities, that is jump points, plus interval. Okay, like a continuous interval. If these two like are following, then that type of random variable is categorized as mixed random variable. Okay. And in that case, the property is like satisfied in such a manner. Summation is also there, plus integral is also. This comes out to be one. Like if we are given any random variable, and a function is defined on the basis of those random variable. Okay, then if we like integrate or some taking summation over the given ranges, then it is not going to be equal to 1, because it is not only either discrete or continuous, but it is a mixed version of discrete and continuous. So we use this formula to check whether that is mixed or not. Okay. Okay, we have a very properties of the random variables is also there. Let me write it down. Like the first one is probability. You people have already like seen this. Probability between a random variable x lie between a to b. The probability of this is CDF of at x equal to b minus CDF at x equal to a. Okay. Again, if we are discussing about probability that a b. Here we have considered both a x lies between a and b and including both. Then it is fb minus fa and plus probability that x equals a is there. Okay. In a similar manner, like if we are using open interval ab both, then in that case fb minus fa, and b is not there in this particular range. The b point p is not included in this probability, so we need to also subtract probability that x equal to b. Okay, and these are all satisfied by the discrete random variables. Okay, but if we are dealing with the continuous random variables, the probability, like if x is continuous random variables, in that case the probability of x at a point comes out to be 0. That means the probability at a point is 0 when we are dealing with the continuous random variable. So in that case, either we take or consider the sign equal to or not, both have the similar meaning. Like probability that x lies between a to b is equal to probability that x lies between a to b including a and excluding b. This is also equal probability that we include x lies between a to b both. This is also equal to probability that a, okay, okay, these all have the similar meaning when we are dealing with the continuous random variable. And in case of discrete random variable, these three properties you should like remember. And if we are discussing about the mixed random variable, we need to take all these points in our mind. Okay. So these are some of the properties. Now the last topic is functions of a random variable. Okay. So we have a theorem actually here. We are going to discuss about the functions of a random variable. Okay. Up to now, we are discussing about the random variables and types of random variables. Now, suppose x is a random variable. Okay. And we create some function of this x. Suppose gx is there. Okay, then it is a function of random variable. And if we know about the about x, about the distribution of x, then with the help of those information, we are able to like evaluate the distribution of y, which is a function of the random variable x. So that's why this topic comes here. Okay, so the theorem is like this. Let x be a continuous random variable with PDF. Suppose the PDF will be fx. Okay, the suffix x is for it belongs to the random variable x. If we define a function g which is equal to gx equal to y, if g is a like strictly monotonic function and differentiable as well, and differentiable, then the PDF of random variable y, which is a function of the random variable x, is like here we have written y. So the PDF of y is defined as like the PDF of x at g inverse of y. So here y equal to gx, so x equal to g inverse of y. So we have write the x, or we replace the x with g inverse of y here. Okay, g inverse of y multiplied by the dd y of g inverse of y. Okay, this happens when y equal to gx follows and 0 otherwise. Okay, so when when we define the functions of the random variable in such a manner that that function is strictly monotonic and differentiable. Okay, so we will directly use this formula to find or to evaluate the distribution of uh, random variable y. Okay. Okay, now we have some questions. So let's start or discuss some questions on these topics. If anyone have like anything they want to like again discuss or not able to understand till now, we can discuss here. Okay, these are some of the like the topics we have discussed in the second week. So we are now going to solve questions based on these topics. Anyone? Okay, then I have written some questions. Let's discuss about these questions. Okay, so the question one will be like the CDF of a random variable x is given by. The question is this: the cumulative distribution function of a random variable x is given by. We have some options here like fx equal to probability that x is greater than or equal to x. Option B will be like fx equals probability that x equal to x. C will be like probability that x, sorry, fx equal probability that x is less than or equal to x, and D is like fx equal to probability of x is greater than x. Can anyone tell me which is the correct answer for this?
C.
Hello?
C. C.
Okay. Anyone who have different answer? It's actually definition. We have discussed like it is a cumulative distribution function. So up to that point or before that point, the probability up to that point and before that point. So x or less than x. Okay, so it is the right answer. Okay, we have one more question. The CDF of a random variable must be. Okay, this is discussed now, but let me write. The CDF of a random variable must be monotonic, and we have four options here: increasing, decreasing, non-increasing, and non-decreasing. So what will be the right answer?
D.
B.
D. D.
D. Okay. Non-decreasing and increasing. What is the difference between non-decreasing and increasing? Can anyone tell me? Hello. Non-decreasing means it may possible like f of x1 equal to f of x2, na? Less than or equal to. Okay, increasing. Suppose it is an increasing function. This implies f of x1, f of x2. Okay, x1 is less than or equal to x2. Then f of x1 is less than or equal to f of x2. Okay, so it is an increasing, strictly increasing actually. Okay, in short, increasing. But when we are discussing about non-decreasing, so it is not going to decrease, either increase or not. So equal to is also there only. Okay. Now we have a question. Suppose the PMF of a random variable x is defined as, suppose the probability mass function of a random variable x is defined as probability that x equal to x 1 by 5, x equals 1, 2, 3, 4, 5, and 6. Okay, and 0 otherwise. So is it which type of random variable x? Okay, our question is determine the type of random variable. Determine the type of random variables. Okay, so we have option like discrete, continuous, mixed, or like we can say that not a valid function or random variables. So like how can we define? Can anyone tell me what should be the answer? Anyone? Actually, look, here I'm writing it wrong. One thing I hope you people may say, but no one said. Look, here we have defined the probability at x equal to 1 by 5 and x equal to 1, 2, 3, 4, 5, 6. So it is a PMF. I am claiming that it is a PMF. So 1 by 5 for x equals 1, 2, 3, 4, 5, and 6. So that must follow the probability 5, which comes out to be 5 by 6 and not equal to 1. So it is not a valid random variable or not a valid probability function. It is okay. The question is like this. I'm just manipulating the question. The question is like 1 by 6. In that case, our first aim to check whether it is a proper PMF or PDF or not. And for those purpose, we use either summation over the entire range of x or the integral over the entire range of x should be equal, must be equal to 1. Okay, so that property satisfied, in that case we are going to discuss about whether it is a which type of random variable. Here we have a discrete, continuous, mixed, and the fourth one is maybe. Okay, so in that case, here we see that only the probability exists at the jump point, either 1 or 2 or 3 or 4 or 5 or 6. Okay, so what we can conclude from here, the probability is only at jump point, so it is a kind of discrete random variable. Okay, so it is a kind of discrete random variable because the probability like occurs at only jump points. If it is it like the probability have jump points and an section of interval or piecewise section of intervals have, then in that case we have continuous and discrete both, so it is a mixed type of random variable. Okay, now the next, okay, everyone know na, understand what I'm telling na? Now the question number 4 will be like okay, let me write it in the next page. The question is like, let omega equal to 1, 2, 3, and let f be a sigma algebra. Okay, such that the random variable x defined in such a way like x of w equal to w plus 5. Some people say the x of omega also. Okay, but since here is already omega, capital omega is also here, so I'm using w term. X of w equal to w plus 5. This is the function we are defined. Okay, is a random variable on the sample space omega and field f. Then find f. Okay, we need to write down all the elements or events of like all the elements in f or all the events of omega. Okay, so can anyone like write it down or can tell me how it calculated? The first one is like we have some options as well. Okay, phi, omega, 1 and 2, 3. There are 4 elements. Now the option B is here. It contains the null set, the omega, the 2 and 1, 3 is there. The option C is like phi, omega. Okay, sorry. 3 is there and 1 and 2. 1 and 2. And the last option is f equal to p of omega. Okay, so what is the right answer and how like the answer comes? Can anyone like try to solve or want to say? Look, we are given na. Let's solve the question. We are given omega equals 1, 2, 3. Sorry, yes, omega. The sample events are this. And the random variable or the function is defined like this. Na? Omega plus 5 is the, yes. Okay, so this omega comes from these value. Okay, so x at omega equal to 1 is nothing but 1 plus 5, 6, x omega equal to 2, 2 plus 5 equal to 7, x omega equal to 3, 3 plus 5 equals 8. Okay, so these three are the possible answers we have. Now, how to define this? We have a map, okay, x. Now the definition says inverse map. So inverse map of x inverse of what? X inverse of 6. This gives x inverse of 6 gives 1. Okay, the one element from the f. This comes from the f. Similarly, x inverse 7 gives 2. It also belongs to f. Okay, so this is the definition part. Okay, the inverse image, uh, the inverse image will lie within the sigma field f. So here 1, 2, and 3. These are the inverse image of 6, 7, 8, which lies in, which should or which must lie within the sigma field f. Okay, so now our sigma field will be like this. See, this is already here, and this should also be here. Now we have 1, 2, and 3. So we have these 5 elements there. Are we done? But it is not the answer. Okay. So indirectly, if you have multiple choice questions, then obviously the answer will be option D. But how it comes out to be option D, we will discuss about it. Since F is a field, F is a sigma field or sigma algebra. So it has some property as well. Like if 1 is there, then its inverse is also there. Sorry, complement is also there. Okay, so 1's complement will be like 2, 3. The 2 is also there, then 1, 3 should also be there. 3 is also there, then 2, 3 will also be there. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Sigma omega is also there. So it's like complement is 5 is there, 5 is there, and sigma omega is there. So these are the 8 possible values which form this F as a uh, sigma field. Okay, and this is nothing but the power set of omega actually, which is also donated by P of omega. So the right option is option D. Okay, the field should be the power set of omega. Okay, is it clear? Now it is simple actually. Okay, we have no options like this, the written in the blue one. So, and for the F to be a sigma field, a valid sigma field, we have the complement of 1, 2, and 3 as well. We can write it down. So it is now the proper sigma field, and it contains the inverse image of 6, 7, 8 as well. Okay, so this is the case. Now, okay, now we have some more questions. Okay, based on the functions of random variables. The question 5 is there. Suppose we are defining like this, a CDF function f 0 x by a or 1 when x is less than or equal to 0, when x lie within 0 to 1, and last when x is greater than or equal to. Okay, we are defining a function capital Fx in such a manner. Okay, now we need to check whether the given function capital Fx is a cumulative distribution function or not. We need to check this. Okay, so for that we have 4 properties. Okay, if any capital Fx, any function is given there, then it should follow the four property. What are those four property actually? The first one will be like it must lie within the interval 0 to 1, including both. Here you can see that like the value, the minimum value is 0 and maximum value is 1. So this condition is satisfied actually. Okay, with the help of the definition only. Now the second is like it should be monotonic, non-decreasing. Okay, so how this comes? So we have considered 2 points x1 and x2 in such a way. Okay, we have taken two value. Okay, here since it is given from x0 to a, so we have taken it at a. So x1 is less than or equal to x2, which lies within 0 to 1. Okay, now f of x1, f of x1 is somewhere x is greater than 0. So f of x1 is x1 by a. In a similar manner, f of x2, so it is x2 by a. Since a is common in both, okay, so f of x1 is directly proportional to x1 value and f of x2 is directly proportional to x2 value. So we may directly say that from here, f of x1 is less than or equal to f of x2. Okay, this implies f is monotonically non-decreasing. Okay, non-decreasing function is this. So second condition is also satisfied. Now the third condition. Third condition will be like limit of x tends to minus infinity of fx equal to 0 and limit of x tends to plus infinity of fx equals 1. Okay. So, okay, then let's see. Limit x tends to minus infinity actually means the minimum value. Okay. The minimum value is 0. So less than 0 is also 0. So we see that like this comes out to be 0 and x of plus infinity. Plus infinity here means a or greater than a. So for any value which is greater than a is the value of the function is 1. So this implies it equals 1. So the third condition is also satisfied. Okay. Now the fourth condition. The fourth condition is continuous to the right. Sorry. That means the function should be right continuous. Okay. For the right continuous, we have like we have 2 points actually. If you see here, we have two jump points, 0 and 1. So we need to check the continuity to the right at x equal to 0 and x equal to 1 both. So now first case we will discuss about at x equals 0. So the continuous for the continuity to the right, x tends to 0 plus, okay, f of x, which is limit of h tends to 0, f of x plus h. Okay, x is greater than 0, na? So greater than 0, for greater than 0, if you see the function x is greater than 0, x by a is there and x equal to 0 is there. So this comes out to be 0 actually. After solving, we'll find it comes out to be 0 only. Okay, and the functional value at x equal to 0 comes out to be At x is equal to 0, it is 0. It is given in the first condition. So f of, sorry, yes, x plus h equal to f of x at x is equal to 0 here. Okay. So it is continuous to the right at x equal to 0. In a similar manner, we will discuss about case second scenario. Okay. In case second scenario, light at x equal to a, at x equal to a. So limit x tends to a plus f of x, which can also be written as like limit h tends to 0 f of a plus h. So with the definition here, a plus h lies within this condition. A plus something, so it is more than a. So for more than a, it is comes out to be 1. So the value, the right hand value will be 1, and the functional value at x equal to a also comes out to be 1. If you can see, x is greater than or equal to a, the value of the capital Fx equal to 1. So here Fx is also equal to 1. So like we can claim that limit x tends to a plus f of x equal to nothing but f of x, which comes out to be 1. So fx function is continuous to the right at x equal to a only. Okay, since like now we can claim that since all the four properties are satisfied, then we say that the given capital Fx function is a proper cumulative distribution function. Okay, we have considered, like we have checked all the four conditions, all the four conditions are satisfied, then it is a proper CDF. If any of the four conditions are violated or more than one conditions are violated, in all those scenarios, this is not a proper CDF. Okay. So till this point, like anyone have any doubt? No. Okay, now we have one more question is there. The question is like a random variable x is defined as follow. Like we have defined a distribution function actually. Okay. 0, 1 by 2, 1 by 2 plus x by 2. The 0 occurs when x lies less than or equal to 0, or when x equal to 0. Okay. Here it is not comes out to be 0, equal to 0, and when x lie between 0 to 1. Okay, we are given this. Now calculate probability that the random variable x between 1 to okay, including both. please just try and let me know the answer. Okay. Am I audible now at least? Hello?
Yes, sir.
Okay. Okay. So please try to solve this question. Okay, we have a random variable x and we define the distribution function. The cumulative distribution function is defined in such a manner like fx or x is less than 0, half at x is equal to 0, and half x to lie within range 0 to half, including both the limits. Okay, so please try and let me know the answer. I'm also trying, but please try. Like we can write this now. I think there is some mistake. I think it is a CDF. No, I think it is a PDF. No, I'm writing it. Okay, okay, yes, yes. There is one mistake. This should be the PDF. Okay, this should be the probability function, not the distribution function. Okay, and we need to calculate this. So for this, we can clearly see it is a mixed type of random variable because it has a probability value at jump point and within the interval as well. So we probability.
13/16.
less than equal to half. Okay. And for the first one is directly taken from the solution. We will get 13/16 is our final answer. Okay. Now we have one more question. Suppose X be a random variable with PMF, with probability mass function, probability that X equal to K of X plus 1, or X equal to 0, 1, 2, and 3. Okay. We need to find K so that the given probability, the given above function is actually a valid probability mass function. Can anyone tell me how to proceed for this question? We need to find the value of K for which this given function is a valid probability mass function. Okay. Look, we have read the probability there. Like if any function is probability mass function, then the summation over X comes out to be 1. Okay. So just try to write this. So we have like summation X from 0 to 3, probability that X equal to X equal to summation X from 0 to 3. The probability value is like K of X plus 1, which now can be, this must be equal to 1 actually. Okay. So this particular formula is 0 plus, if we take X equal to 1, then it comes out to be X plus 1, 2 of X plus 1 plus 3 of X plus 1 equals 1. So this implies 0 plus X plus 1 plus 2X plus 2. Anyone can solve this. 3X plus 3 comes out to be 1. And from here, we will solve the value. And the value comes out to be 6 plus 6X plus 6 equals 1. This implies X equals -5. Okay. I think there is one more mistake actually. Okay. K comes out to be minus. So is it not right now? I think we should write here like minus is there, and maybe I'm writing it wrong. K of X minus 1 is there. Okay. Or 1 plus X may also be fine here. Okay. So here it comes out to be X minus 1, X minus 1, X minus 1, X minus 1 is there. Sorry, it's like taking a wrong. 0 plus X minus 1 plus 2X minus 2 plus 3X minus 3 equals 1. So it is 6X minus 6 equals 1, comes out to be X equals 7/6. Okay, so X equals 7. Okay, I'm forgetting K. No. Sorry. Actually, we need to put the value of X, not the value of K. And I'm putting the value of K instead. Okay, let's try again. I think it's +1 is there then. Because I'm writing here +1. I'm writing only question actually. I'm not writing the answer. That's why. Let's start again. K 0 plus 1 plus k 1 plus 1 plus k times of x equal to 2 plus 1 plus k times of x is equal to 3 plus 1 equals 1. So it comes out to be k plus 2k plus 3k plus 4k equals 1. From here we have 10k equals 1. This implies k equals 1 by 10. Okay, so this is the right answer. I'm I'm putting the value of x in place of k. Okay, so this gives the absurd result actually. So this is the right format. Since we know that the probability, the sum of the probability equals 1, or the integral over the probability comes out to be 1. So with the help of those concepts, we are able to calculate the k value. Okay. Now we have some questions on the basis of transformation of random variable. Okay. So let's, couple of more question is there. Suppose we have a random variable x. Okay, we have a random variable x in such a way that the probability density function is defined like this. We have the okay. Now find the PDF probability density function of y, which is defined as the exponential of x. We need to, it is a function of random variable. So we need to find the PDF of y when we are given the PDF of x. Okay. So like here we see that y equal to e to the 4x. It is nothing but a transformation equation. It's called as, okay, it is called transform equation. So in a similar manner, like y equal to g of x is there. Okay, so here the exponential function is actually monotonic in nature, and it is also differentiable. So it follows the theorem. Okay, it follows the theorem that we have stated before. So we directly use the formula, okay, for calculating the CDF of y, which is a function of a random variable x. So the formula, the theorem will be like this. The CDF of y is the CDF of x, g inverse of y, and d dy of g inverse of y. Okay, this is the theorem. Okay, now we have the transformation equal to y equal to e to the power x. This implies x equals log y. Okay, and dx upon dy equals 1 by y. Okay, so yes, so our value will be like fx of g inverse y. Okay, so fx of g inverse y is like okay, it's a simple value. Na? Here it is only 1 is there actually. So we can, there is no x or y here. So 1 into this particular quantity, Jacobian quantity is there, ddx of g inverse y, which is dx upon dy. This is actually ddy of g inverse of y. Okay, so it comes out to be y, 1 by y. So 1 by y is there. But still, it is not a valid PDF because we have not yet defined the range of y. Okay, so here the range of x is 0 to 1. So uh, when like range of x is comes out to be 0 to 1, okay, so this implies x can be replaced with the help of log y. Okay, so x can be replaced by log of y with the help of transformation equation. Okay, so now taking exponential, so e to the power 0 is there, it is y, it is e to the power 1, and this comes out to be 1 to e. Okay, so our final version, final PDF will be like this: 1 by y when y, sorry, when y lies between 0 to 1 to e and 0 otherwise. Okay, so we have the information about the random variable x, and with the help of the random variable x, a function of the random variable, which is y, defined as e to the power x, we are able to calculate the PDF of y. And the final PDF is written here. And yes, we will always use the support, the range or the support also. Okay, maybe sometime it may change and sometime it may not be changed, but we need to check the range for the PDF as well. Can anyone have any doubt in this like transformation? Okay, I have one more question. Okay, the question is like we are given the PDF again, 2x when x lies between 0 to 1 and 0 otherwise. We need to find the probability density function of the random variable y, which is defined as a function of random variable x as 8x cube. So everyone, please just give it a try and let me know the CDF or PDF of the y, this y random variable. Just try once with yourself. Okay, with the similar approach. Since it is a look, let me give you one thing. Since it is a x cube function, which is a polynomial function, so it is differentiable, and cube function is there, so there is no negative, so it is monotonic in nature as well. So y equals 8x cube is actually monotonic in nature as well differentiable. As well as differentiable. Okay, so we can use the theorem to find the CDF PDF of y. Okay, so please try and tell me the CD PDF of y. Hello. Here we can like see na, ki we are given the transformation equal to y equal to 8x cube. So from here we will uh, we will transform x in terms of y, which comes out to be half of y to the power 1 by 3. Now the differentiation of x function is 1 by 6 y to the power minus 2 by 6. Okay. And also the range is like, since x lies between 0 to 1, we replace x with half of y to the power 1 by 3. This comes out to be lie between 0 to 1. And after simplification, we will get y to the power 1 by 3 lies between 0 to 2. And this implies y lies between 0 to 8. Okay. So our range changes from 0 to 1 for x to 0 to a for y. Now the the PDF of the y variable is like, since here it is 2x, 2 into x is there. So 2 into x. X is nothing but 1 by 2 to the power 1 by 3. Okay. Into dx upon dy, which is 1 by 6, 1 by 6 y to the power minus 2 by 3 for y lies between 0 to 8. And after solution, we will get 1 by 6 y to the power, here it is 1 by 3, minus 1 by 3 when y lies between 0 to 8 and 0 otherwise. Is it right, or someone have different answer? Anyone? Can anyone perform the question or not? At least tell me this so that I should proceed. Okay, no problem. See, this is how we are able to calculate or find the functions, find the PDF of functions of random variables. Okay, with the help of the theorem that I've already discussed in the previous slides. Okay, if the functions are, if the transformation functions are continuously differentiable or monotonic in nature, then we will directly use that function, that theorem. With the help of the theorem, we are within a minute, we are able to find the CDF of the functions of random variable. Okay, there are some more transformations are there that we will maybe discuss in further classes. Okay, so like, anyone have any doubt or query or want to ask anything, they can ask, or like we should conclude our session here. Okay, anything to ask?
No, sir.
Okay, okay. Okay, then everyone please try to submit the assignments. Okay, I think the due date of the assignment is 5th of Feb. Okay, and you people may ask any question if you want via my social accounts. Like, I have already LinkedIn account is there, YouTube account is also there. Okay, so you people please watch the videos. Okay, that are already shared with you by the NPTEL team. And if you people haven't registered yet, please register for the exam if you wish to giving the exams. Okay. Okay, then thank you everyone for joining. Let me stop the recording.